If you drop a rock, it'll fall on a straight line path to the ground below. If you move your hand horizontally as you let go, the stone will land farther away. What would happen if the curvature of the path matched the curvature of Earth? An Earth satellite is a projectile moving fast enough to fall continually around Earth instead of into it. On an imaginary tiny planet, you wouldn't have to throw the stone very fast to make its curved path match the surface curvature. Because of the planet's small size and low mass, if you threw the stone just right, it would follow a circular orbit. How fast would the stone have to be thrown horizontally for it to orbit Earth? A stone dropped from rest accelerates 10 meters per second squared and falls a vertical distance of 5 meters during the first second. In the first second, a projectile will fall 5 meters below the straight line path it would have taken without gravity. In the curvature of Earth, the surface drops a vertical distance of nearly 5 meters for every 8,000 meters tangent to its surface. The orbital speed for close orbit around Earth is 8,000 meters per second, or 8 kilometers per second. That's 18,000 miles per hour. At that speed, atmospheric friction would burn an object to a crisp. A satellite has to stay 150 kilometers or more above Earth's surface to keep from burning due to friction. In circular orbit, the speed of a satellite isn't changed by gravity. Compare a satellite in circular orbit to a bowling ball rolling along a bowling alley. Gravity acting on the bowling ball doesn't change its speed. Gravity pulls downward, perpendicular to the ball's motion. The ball has no component of gravitational force along the direction of the alley. Speeds of the bowling ball and the satellite aren't affected by the force of gravity because there's no horizontal component of gravitational force. For a satellite close to Earth, the time for a complete orbit around Earth, its period, is about 90 minutes. For higher altitudes, the orbital speed is less and the period is longer. Communication satellites are located in an orbit 6.5 Earth radii from Earth's center, so that their period is 24 hours. This period matches Earth's daily rotation. They orbit in the plane of Earth's equator, and they're always above the same place. The Moon is farther away and has a 27.3-day period. The International Space Station, ISS, orbits at 360 kilometers above Earth's surface. Acceleration toward Earth is somewhat less than 1 g because of altitude. This acceleration, however, isn't sensed by the astronauts. Relative to the station, they experience 0 g. An ellipse is the closed path taken by a point that moves in such a way that the sum of its distances from two fixed points is constant. The two fixed points in an ellipse are called foci. For a satellite orbiting a planet, the center of the planet is at one focus and the other focus would be inside or outside the planet. Satellite speed varies with an elliptical orbit. When the initial speed is more than 8 kilometers per second, the satellite overshoots a circular path and moves away from Earth. It loses speed due to the pull of gravity. The satellite slows to a point where it no longer recedes and begins falling back toward Earth. The speed lost in receding is regained as it falls back. The satellite then rejoins its path with the same speed it had initially. The procedure repeats over and over, and an ellipse is traced each cycle. The parabolic paths of projectiles such as cannonballs are actually segments of ellipses. For relatively low speeds, the center of Earth is the far focus. For greater speeds, the near focus is Earth's center. When the projectile traces a circular orbit, both foci are together at Earth's center. Moving objects have kinetic energy. An object above Earth's surface has potential energy due to its position. Everywhere in its orbit, a satellite has both KE and PE. In a circular orbit, the distance between a planet's center and the satellite's center is constant. The PE of the satellite is the same everywhere in orbit. By the law of conservation of energy, the KE is also constant, so the speed is constant in any circular orbit. For a satellite in circular orbit, no force acts along the direction of motion. The speed, and therefore the KE, can't change. In an elliptical orbit, both speed and distance vary. The apogee is the point in Earth's orbit farthest from the center of Earth. The perigee is the point in the satellite's orbit closest to the center of Earth. The PE is greatest when the satellite's at the apogee and least when the satellite's at the perigee. The KE will be least when the PE is most, and the KE will be most when the PE is least. At every point in the orbit, the sum of the KE and PE is constant. When a payload is put into Earth orbit by a rocket, the speed and direction of the rocket are very important. If the rocket were launched vertically and quickly achieved a speed of 8 km per second, it would soon come crashing back at 8 km per second. To achieve orbit, the payload must be launched horizontally at 8 km per second once above air resistance. The initial thrust of the rocket lifts it vertically. Another thrust tips it from its vertical course. When it's moving horizontally, it's boosted to the required speed for orbit. Neglecting air resistance, fire anything at a speed greater of 11.2 km per second and it'll leave Earth, going more and more slowly but never stopping. How much work is required to move a payload against the force of Earth's gravity to a distance infinitely far away? The value of PE for a 1 kilogram mass infinitely far away is 62 million joules. To put a payload infinitely far from Earth's surface requires at least 62 million joules of energy per kilogram of load. A KE per unit mass of 62 million joules per kilogram corresponds to a speed of 11.2 kilometers per second. This escape speed is the minimum speed necessary for an object to escape permanently from a gravitational field. The escape speed from the Sun is 620 kilometers per second at the surface of the Sun. Even at a distance equaling that of Earth's orbit, the escape speed from the Sun is 42.2 kilometers per second. A projectile fired from Earth at 11.2 kilometers per second escapes Earth but not necessarily the Moon and certainly not the Sun. The first probe to escape the solar system was launched from Earth in 1972 with a speed of only 15 kilometers per second. The escape was accomplished by directing the probe into the path of Jupiter. It was whipped around by Jupiter's great gravitational field, picking up speed in the process. Its speed of departure from Jupiter was increased enough to exceed the Sun's escape speed at the distance of Jupiter. Pioneer 10 passed the orbit of Pluto in 1984. Unless it collides with another body, it'll continue indefinitely through interstellar space. Escape speed refers to the initial speed given to an object, after which there is no force to assist motion. But we could escape Earth at any sustained speed greater than 0 if you give it enough time.